Very good evening, everyone, and thank you, Dr. Bala Bhaskar and team, for providing me this opportunity and presenting the topic, which is core for every anesthetist practice. And the topic of presentation is basic physics for a practitioner using anesthesia machine. If you go to the history of anesthesia machine, Morton was the one who publicly demonstrated the inhalation of ether in 1846. And subsequently, more complex inhalers were developed to allow the inhalation of multiple anesthetic agents. And anesthetic flow was independent of patient inspiration of this. And these were portable apparatus. Later on, modification to these Bartholomew apparatus and head-wing apparatus led to the invention of Boyle's machine by Henry Edmund Gaskin Boyle in 1917. And this was first made by under the direction of Lord George Wellesley, and which was later acquired by British Oxygen Company. But Boyle was a trade name of VOC, and it was named so to respect the inventor Boyle. With the advent of new technology, new vaporizers, incorporation of new electronic technology into the Boyle's machine, came the machines which we are nowadays using in everyday's practice, and I think every one of us is using those machines only, like Traeger and Reflex. An anesthesia machine basically receives high pressure compressed gas from the supply source, creates gas mixture of known composition and flow rate, and deliver this gas mixture to the patient at safe pressure. And what is the source of these gases? The main central source of supply is either the large cylindrical tanks, or cylinder manifold, or liquid oxygen tank known as cryogenic liquid system. And some larger hospitals may include the on-site production of plants also. Gases are stored under high pressure in tanks or cylinder manifold and then released and regulated via special controlled equipment, which is further then distributed via cylinders and pipelines. Cylinders are the containers which again store gases in either liquid form or gas form or in both state depending on the physical properties of gas. The gas is then supplied to the various terminal units and in the OTs and wards through pipeline and cylinders. Now, this is basically a schematic diagram of an anesthesia machine, and which can be conveniently divided into high, intermediate, and low pressure system. High pressure system is basically receiving gases at cylinder pressure, reduces the pressure, make it more constant to use, and the intermediate pressure receive gases from the regulator or hospital pipeline system, and then delivers them to the flow meter or oxygen flush valve, and the low pressure system, which takes gases from the flow meters to the machine outlets and also contains the vaporizers. So let's go to the physical principles now, because the pressure is one most important physical principle which we all should know. And what is pressure? Pressure is basically the amount of force that is applied over a certain area. If it's pounds per square inch, we call it as a PSI, or newtons per square meter. So all the stored gases in cylinder are exerting pressure on the wall, and that pressure is measurable. The PSIG is basically pressure pounds square per inch gauge. This basically refers to the pressure above atmospheric pressure, where the pressure gauge is 0 to atmospheric pressure. PSIG is synonymous to PSI. 1 atmospheric pressure is equal to 100 kilopascal, 14.7 PSI, and these are the conversion of 1 atmosphere to various other SI units of pressure. The atmospheric or the contained gas, that is a partial pressure, these units are expressed in the terms of millimeter mercury or centimeter water. Now, to understand how the gas is stored, we should know about the critical temperature. A gas is either stored as a liquefied form or in a non-liquefied form. The liquid gas is basically under a pressure at normal temperature. It maintains liquid gas equilibrium, and as gas is removed, enough liquid evaporates again into vapor, keeping the pressure constant and maintaining the equilibrium. The gases which are kept in liquefied form are the nitrous oxide and carbon dioxide. While the non-liquefied gases like nitrogen, oxygen, they are basically gases and they are kept under high pressure at normal temperature. They can become liquid only at very low temperatures, or that is a principle of cryogenic plant. Now, critical temperature is the physical principle which will tell you that why some gases can be liquefied and why some cannot. So it is basically temperature of a substance at and above which vapor of the substance cannot be liquefied no matter how much pressure is applied. So if this line is your critical temperature, you can see that we are applying pressure, but there's only gas formation. There's no liquefaction is happening. And once it is below critical temperature, the pressure is being given there, and you can see the formation of liquid in the chamber. So this is the importance of the critical temperature. Now, critical temperature of oxygen is minus 118 degrees. So at the room temperature, it remains as a gas. So to cool, when you cool it up to the level of minus 118 or below it, then only it can liquefy and we can store it as a liquid. And that is the reason that why liquid oxygen should be stored below minus 118 degrees Celsius. Nitrous is 36.5 degree critical temperature. So it exists as a liquid at room temperature and can exist as a gas over this temperature. So that means the importance is the right temperature. The right temperature is required to liquefy a gas. And critical pressure is the pressure which is exerted by a gas at the critical temperature, or the pressure which is required to liquefy the gas at the critical temperature. So this is the principle behind the cryogenic plants, which are also called as a vacuum insulated evaporators or cryogenic liquid system. 1 liter of liquid oxygen can give 80-60 liter of gas at 20 to 90 psi. So it's a cheap and large amount of gases can be produced. This is basically a tank, which is an insulated vessel. The outer layer is made up of chrome steel and inner is of the stainless steel. And there's insulated by a vacuum. And this vacuum basically obstructs the heat transfer from the exterior. And the gas above the liquid oxygen, then passes through the steam passes through this superheater, and the temperature is raised, it evaporates and then goes into the pipeline system. While the liquid is, when suppose you need a lot of oxygen, the requirement is more, then the liquid oxygen is drawn off from the bottom of the VAA and it passes through the evaporator, and the gas is then enters directly into the pipeline system. And the maximum pressure is 10.5 bar. If the pressure goes above 17 bar, the oxygen escapes via safety valve into the atmosphere. This is the safety valve. What are gases and vapor? The gas is basically, which is gaseous at room temperature and pressure. That means the room temperature is quite above the critical temperature, and that's why it can remain in the form of a gas. While vapor is that when a gas coexists in equilibrium with a corresponding liquid, the gas is termed as a vapor at room temperature. That means the critical temperature during this vaporization, the room temperature is quite low to the critical temperature. And what is vapor pressure? Vapor pressure is a pressure which is exerted by a vapor in equilibrium with its liquid at a given temperature in a closed system. When it represents the maximum pressure the vapor can exert at that temperature, it becomes saturated vapor pressure. So what is the implications of knowing about these gas and vapors on filling of cylinders and measuring the content of cylinders? Now, cylinder pressure will be indicative of its volume only if its content are in gaseous state. So if we look at this oxygen cylinder, we can see that this full is going towards the left, it is becoming empty. And we can see that the pressure gauge and the volume, they are correlating linearly. So approximately the full cylinder is 660 liter of gas. And at 50% full, when the pressure is half, the volume is also half. So it is basically the pressure gauge readings are reflecting the amount of oxygen cylinder because it is in the gaseous state. What happens to the nitrous cylinder? Does it reflect the content of the nitrous cylinder? The pressure gauge here, you will see that it will not reflect the content of the nitrous cylinder. Now, this full nitrous cylinder containing 1590 liter of gas and the pressure is 750 psi. Now, you can see that the cylinder is getting used up. It is half here, it is around 1/4 here, but the pressure is remaining constant at 745 psi. And here, when a whole of the liquid has been evaporated, it has become vapor, the gas is left, and gas is now rapidly being consumed by the patient. Now the pressure has decreased and it is showing the empty cylinder. That means the laws which were applicable previously in the oxygen cylinder are not applicable here. And so the pressure of the gas above liquid remains independent of how much liquid remains. So the pressure gauge is not reflecting the content of nitrous cylinder. This is the same thing. Now coming to the filling ratio. Now What is filling ratio? There is a limit to the amount a gas cylinder can hold. So oxygen cylinder was a cylinder with a pressure of 2000 psi. It's at room temperature, while nitrous oxide shows a pressure of pressure of 745 psi with vapor and liquid at its equilibrium. Now, surface pressure is the pressure which a maximum pressure to which a cylinder can be filled at 70 degrees Fahrenheit or 25 degrees centigrade. Now, you should know that the liquid is less compressible as compared to gas. So we cannot fill the gas. We have to partially fill it because there's always a risk of overfilling and potential explosion due to temperature changes. So because as temperature rises, the liquid expands. So what is filling ratio? Filling ratio is basically the weight of the gas in the cylinder to the weight of water that can be held by a cylinder, or the weight of water that would fill the cylinder. So this is the filling ratio. Now, filling ratio of nitrous and carbon dioxide, which are the liquefied gases, that is 0.75 in the cooler climate. That means if a cylinder can hold 100 liters of water, the 75 liters of nitrous oxide can be filled in it. In the tropical climates like India, the filling ratio is 0.67. So can this filling ratio help you know about knowing the content of liquid nitrous in a cylinder, in a E-type cylinder especially? Suppose, for example, the weight of a liquid nitrous in an E-type cylinder with 5 liters of volume is we know that what will be the weight of liquid. Now we know that the filling ratio is 0.67. The 5 liters of volume will take about 5 liters of water. 5 liters of water being density 1, it is equal to 5 kg of water. So if you multiply this with the filling ratio, it comes about 3.35 kg. So weight of liquid nitrous that can be filled in E-type cylinder is 3.35 kg. For non-liquefied gases like oxygen, we are not supposed to exceed the service pressure, but 10% is allowable from the tested pressure. Coming to the Boyle's law. Boyle's law is very, very important and useful for us to determine the volume of any gas at any given pressure in cylinder. Basically, it is a relationship between pressure and volume. Pressure and volume is inversely proportional to each other. As pressure decreases, volume increases. And when pressure is increased, volume decreases. But the temperature is constant, always have to be kept constant. So P is inversely proportional to V. P is equal to K is a constant here, and if we convert into equation, it becomes P1 V1 into P2 V2, where P1 and V1 are the initial pressure and volume, and P2 V2 becomes the change pressure and volume, and this has to remain constant. So the equation comes like this. So now we will apply this Boyle's law to determine this based on pressure gauge reading. Now, what is the oxygen content of a full E-type cylinder at 15 psi? Now, E-type of cylinder, the volume is around 5 liters. Service pressure is full, 2000 psi. So the volume of oxygen available V2 we have to calculate at P2, which is 15 psi. We know the equation. We'll put these values in the equation, and this after multiplication division, it will come around 665 liters. So next question arises is how much it will last if we use oxygen at 5 liters per minute. We will just simply divide it, and it will come in minutes, and we can get it the hours we expect the cylinder to get exhausted. I think I'm clear here. This law is not applicable when we have to calculate the content of nitrous oxide in E-type of cylinder for use. One is the Avogadro's law. Here we use the Avogadro's law. So Boyle's law does not apply here. Boyle's laws only apply when whole of the vapor has been evaporated and gas is left. So till your cylinders are showing constant pressure, the law applicable will be Avogadro's law. And it basically makes two statements that the equal volume of all gases at the same temperature and pressure have got the same number of molecules. And 1 mole of any gas or vapor occupied 22.4 liter at sticky. That means the 1 mole of nitrous, that is 44 gram, 32 gram of oxygen, and 28 gram of nitrogen are carrying same number of molecules, and they all are occupying 22.4 liter at standard temperature and pressure. That is what I have written is 1 mole is equal to molecular weight or gram molecular weight will contain 6.023 into 10 raised to power 23 molecules. This is Avogadro's number. And they all will occupy 22.4 liter at standard temperature of 273 Kelvin and 760 mm Hg. Now, how does we apply it? So for the nitrous cylinder, we need to know the weight of the cylinder. Total weight of the cylinder minus tire weight, that is the empty cylinder. Now let us take an example. So the total weight of cylinders was 5.6 and the empty cylinder weight come out to be 4.5. So weight of nitrous definitely is 1. We subtract it is 1.1 kg or 110 grams. So according to Avogadro's law, the 45 gram of nitrous was occupying 22.4 liter. So what with the 1100 grams, it comes out to be 560 liter. So this cylinder will have 560 liter of nitrous oxide in this. And how much will it last? Again, if we divide it, we'll get the minutes or hours. This is basically a table which is showing different type of cylinder size of oxygen and all type of cylinders available. The main thing which you have to remember here is the most common cylinders being used in OTs and wards are the E type, while G and J are the one which are used in the cylinder manifolds, and the volume is 680 liter, while F, then it is increasing in the proportion only. Oxygen pressure 2000, nitrous 750, this I already have discussed. What is adiabatic process? Adiabatic process is basically a thermodynamic process where no heat can be exchanged between a system and its surroundings. So how does this change happen? This change only happens when the process is being very fast or the system is perfectly insulated. So how the system internal energy is changing then? The system internal energy is changing solely based on the work done on or by the system. It is taking up the heat from the system only. So should we, as an anesthetist, should learn about adiabatic process is while we are opening the oxygen cylinders. We should always open up the oxygen cylinders slow, not the rapidly, because whenever we open the cylinder rapidly while attaching it to the anesthesia machine, this rapid flow of gas into the narrow space, it goes into the yoke assembly. And that is a narrow tubing. It will cause rapid recompression of oxygen in that narrow tube, producing a very high temperature because of the adiabatic process. And if there are a lot of gases or dust particles there, there's a possibility of possible explosion. So it is crucial that we open the valve slowly to prevent the rapid buildup of pressure and prevent ignition of particles. What is the role of Entonex? What happens if Entonex cylinder is placed in a cold climate? Now, Entonex is a mixture of 50% mixture of oxygen and nitrous. Every one of us, we know that. Now, here important is the critical temperature of oxygen is minus 118, and while the nitrous is 27 degrees. So what happens when we mix them? When we mix them, the critical temperature of the mixture becomes minus 6, and this is called as the Poynting effect. Poynting effect is basically when your mixture, it becomes a mixture of gases, and they exhibit the physical properties which are different from the individual gases, including the boiling point and the critical temperature. And that's what happening here. But this temperature is called as a pseudo-critical temperature here. So above pseudo-critical temperature, it will remain as gases, both of them, but below the pseudo-critical temperature, whenever especially in the cold climates, what will happen? They will start separating into their own individual components, which nitrous will start liquefying. So if temperature is below minus 6 degrees, the nitrous will liquefy and will remain in the bottom of the cylinder. Now, oxygen being in the gaseous state will be taken up by the patient. There will be no analgesia, but now it will taken up rapidly. Now, what is left is nitrous. So the patient will take up the hypoxic mixture, and that is really, really dangerous. So all the Entonox cylinders should be placed in a side. They should be not placed vertically. They should be thoroughly shaken before use, and they should be stored above 10 degrees centigrade to maintain the pseudo-critical temperature. Why oxygen cylinders should be kept in shades? Another law comes here into the picture, that is Gay-Lussac's law. And Gay-Lussac's law said that at constant volume, the pressure is directly proportional to the temperature. So means if pressure increases, there is increasing temperature, pressure will increase, keeping volume constant. So what happens? It can cause explosion. So that's why that's why the oxygen cylinders should not be kept in sun. They should be kept in shades. There are a lot of safety features which have been provided, like fusible plugs. Basically, it's a metal which is made up of, it's an alloy of cadmium, bismuth, tin, and lead, and the yielding temperature is 202 degrees Fahrenheit. Will save the cylinder till that temperature. Then there's a frangible disc where the diaphragm breaks at a particular pressure and the gas is vented out. Similarly, there's a spring-loaded valve or safety relief valve. These all are the basic safety features to prevent bursting of cylinders. Now, this is your modern machines. This is basically like a cockpit where it integrates a lot of components, both electrical and pneumatic system. The electrical system and pneumatic system. Pneumatic system includes the high pressure, intermediate, and low. I'm not going into the details of electrical system. High pressure system I've already discussed. It is starting with the cylinder at 2000 psi and ending at the regulator at 45 psi. And The high pressure system, cylinders are included in the high pressure systems. While in the intermediate system, the pipeline is included. So pipeline is regulated at 55 psi, while cylinder is at 45 psi. And this all are the components of the intermediate system. Low pressure system is downstream to flow control valve, and it includes flow meter, vaporizers till the common gas output. Now coming to, I'll pick up the physical principles of some important parts of anesthesia machine. I cannot pick up each and every one because of the paucity of time. So first is a check valve assembly. This is a part of high pressure system. And this basically works on the principle that when downstream pressure is more than upstream, the valve will close to prevent the backflow. How? Now, this check valve basically assembly is at this point. After one cylinder is connected to the machine, it ensures one-way movement of gas. Now, how? When the inlet pressure is more, you can see this diaphragm is moving downward and it is allowing the gas to come inside. Now, when this inlet pressure is, this outlet pressure is becoming more, like all the upstream pressure is more, the seat is closed and valve is closed and no gas can move out. So basically, this is just ensuring the unidirectional movement of gas. It is preventing gas transfers to the cylinder. It is also allowing the cylinder change without unmounting the other one. Next important is the pressure gauge or the Borden's gauge. The Borden gauge basically measures the pressure of a gas within a closed system and displays it in units like PSI, bar or kilopascal. This is for the cylinder. This is, we can see in the front panel of the machine. Even now, LED-based pressure gauges are there, which shows different type of lights if the cylinders are open or empty or open or have adequate pressure. So this is a LED panel. It works on the principle of basically, there's a hollow metallic curved flexible tube, this one. It is sealed at one end and other is fixed to the pressure source, it is cylinder. So as pressure increases, the tube tries to uncoil this like this. And this movement is then transmitted to the pointer via mechanical linkages in gear. And this measures the reading, which we read on the pressure gauge. And it tells the content of the cylinder. So the pressure gauge is color coded. For oxygen, it is white and blue for nitrous. Next is a pressure regulator. This is also part of your high pressure system. And it's very, very important part because it reduces the high pressure in the cylinders to a lower and more constant pressure to maintain a constant flow. So this is your gauge and this is your pressure regulator we can see in the picture, or this is with the cylinder. Sorry. So we need this reduction in pressure, constant pressure to control damage to the flow control valves or to prevent barotrauma to the patient lungs. Even with the lowered pressure, the fine adjustment of the flow meter is possible. These are called as the fixed pressure regulators because the orifice is fixed here. Oxygen cylinders, they decrease the pressure from 2200 psi to 4560, while nitrous, it reduces to 45 to 60 psi. The basic principle which works here is that force is equal to pressure into area. As we know that the pressure was force among area, which we just convert, equation is now force is equal to pressure into area. So one thing you have to remember that if there are no pressure regulators, the anesthesiologist will keep on readjusting the flow control valve to maintain a constant flow because the cylinder pressure is getting used up and the amount content is decreasing with time, decreasing the flow. So what is the principle here? The principle here which comes in picture is this equation, which says that this pressure is dependent on area. So these are the valves. Here you can see that the force is kept constant with it is a spring which is providing force, and force is kept constant with the spring. And this is the high pressure value inlet and this is a low pressure outlet. Now we have to keep these two pressure constant. Now what has been done here, that area has been increased by using the diaphragm here. So when area inside the regulator has been increased using the diaphragm, so automatically the pressure would decrease based on this equation. But the manufacturer has kept the outlet pressure fixed. So the decrease in pressure because of increase in area will bring the outlet pressure low. Now what happens when the inlet pressure is reduced? Now this spring will exert more pressure, increasing the output pressure, keeping this equation constant. So when pressure is decreased, here pressure is decreasing because of increase in area. And here spring is exerting pressure to bring the output pressure to the constant rate. In certain new machines like Datex, Omda, and Draeger, there are some second stage pressure regulators and flow restrictors are there. Datex has got the second stage pressure regulators, which works on the same principle as discussed, while the Draeger shows the flow restrictors. And it works on the Bernoulli's principle. We all are aware of this principle that whenever a gas flows through tube, encounters a restriction, at that point the pressure drops and the velocity increases. That is, the kinetic energy increasing and potential energy is decreasing. So these second stage pressure regulators are located upstream to the flow meters, and they are basically decreasing pressure of nitrous up to 26 psi and oxygen to 14 psi. This is a diameter index safety system. This is basically the pipeline inlet connections, and these are, these are very secure connections, so that the connections, there should not be misconnections of any cylinders. And there are two concentric pores like BB and CC on the body, which fits into the MM and N in the nipple and making this alignment. And after this alignment only, the thread and connectors, these thread and connectors will engage properly. So we can commonly see in wards and OTs like these oxygen, nitrous oxide, and air connectors are there. But what are the oxygen failure protection devices? In older machine, there was a master-slave regulator where the nitrous pressure regulator acted as a slave while the oxygen acted as a master regulator. And the physical concept behind was that the nitrous pressure regulators were constructed in such a way that the minimum pressure of the oxygen flow was required to release the flow of nitrous oxide. But this was not a foolproof method, and hypoxic mixtures were given to the patients even after this oxygen failure protection devices. So another proportionating kind of safety mechanisms has now been incorporated, like pressure sensor shutoff valve, which is in the Datex, and another is oxygen failure protection device. Now come to this picture on the left side. Now this pattern, which is pressure sensor shutoff valve, is basically working in a threshold manner. Either this valve is open or shut. Now what happens? The oxygen supply, your pressure is more than 20 psi. The gas is going inside. Its pressure is high, normal. So an oxygen supply from the supply source is fine, which is going to the flow meter. Now this oxygen supply pressure goes less than 20. Now this is totally cut off. No nitrous oxide can be seen there. So it's either open or it's shut. So piston is working only at the pressures of 20 psi. Now what happens in the oxygen failure protection device? It works in a proportionating manner. It depends on the oxygen. Now, suppose oxygen supply here is less than 50 psi. Your the nitrous is moving fine at the 50 psi. Fine, this is good. Now, the pressure is decreased to 25 psi. This needle has come downward, decreasing the supply to half of nitrous. Now, oxygen supply is decreased to 0. This is completely shut off. So, Draeger is basically working on the principle of proportionating, and the supply of nitrous and other gases are cut off usually when oxygen supply goes below 12 plus minus 4. What is the physical principle behind oxygen flush valve? We all have used it, and we know that we use it in the emergency purpose only. Basically, what happens is there's a direct tube which connects between the oxygen pressure regulator, like this is oxygen, and this is the tube which is directly connecting to the oxygen flush. So means the vaporizers, flow meter, all these are bypassed. So whenever there is an emergency, we need to use the oxygen flush button. That means it is supplying directly pressurized oxygen from the pipeline and cylinder pressure regulator at 35 to 70 per liter minute to the common gas outlet. The problem is barotrauma, because the flush valve is allowing fresh gas to enter the breathing circuit at a rate of approximately 1 liter per second. And another is awareness, because your anesthetic agents are being diluted now. Now coming to the flow, principle of flow. The flow is the movement of gas or liquid through a system per unit time. Okay. And it depends on the pressure difference basically. Now there are two types of flows. One is the laminar flow, another is turbulent. The laminar flow you can see is smooth, orderly. The particles usually move in parallel layers. The peripheral layers move slow because of resistance, which is encountered due to the wall, and the center particles move faster. The principle which helps to calculate laminar flow is Hagen-Poiseuille law. Q is the flow here, and it basically depends on the pressure difference, radius to the power of 4, and it is inversely proportional to the viscosity and length of the tube. So the Hagen-Poiseuille law, viscosity is a predictor. You have to remember here. Okay. Coming to the turbulent flow, it is total non-parallel, non-orderly. They are just going here and wire. The particles are going here and there. So turbulent flow, because of this tumbling effect, all the molecules in system, they encounter to the wall of the tube. So why this is important for us? The turbulent flow, anywhere there is a restriction or constriction, like curves or bend or walls, we encounter this kind of a turbulent flow. So what laws is followed here? The Hagen-Poiseuille law doesn't work here. The Graham's law for turbulent flow, which is basically directly proportional to the change in pressure and inversely proportional to the density, square root of the density. So in the turbulent flow, to calculate the flow, density plays a role, which is another thing which we have to remember. So how do we decide that which flow is turbulent or flow? That is basically decided by a Reynolds number, that is a dimensionless number. And this is basically dependent on the density of fluid, velocity of fluid, and these are the parameters. Now, whenever it is above 44,000, that means the flow is turbulent. When it is below 2,300, the flow is laminar. In between 3 to 4,000, we say that there's a translational form, laminar going to become turbulent. Now, this Graham's law of turbulence is also applicable in anesthesia practice for the use of Hilliard's. Because as I told you that the Graham's law turbulence is inversely proportional to the density. So if density is decreased, flow will increase. So this is a principle which is used when there is a respiratory tract obstruction. So flow is turbulent, and heliux, which is 79% helium plus 21% oxygen, it is density 6 times less than air. So now, because it is dependent on the density of gas, if you use less dense air, flow will be more. That is the principle behind the use of heliux. Now, another use of these laminar and turbulent flow comes into picture when we talk about flow meter assembly. This is every one of us, day and night, we're using this flow meter assembly. And we know that there's a flow control knob there. There's a needle wall which regulates the flow via tapered orifice. There's a flow tube called Thorpe's tube. Then there's a bobbin or a float which can be a ball also. Then there are calibrated markings on a scale. And there is stopper or a glass plug to prevent the float from escaping the top. Now, two principles work here for preventing the mixture of oxygen and especially to prevent the hypoxia basically at the level of flow control valve. One is a link 25. It is a principle which is followed in DATEX on the trolleys. And what happens is you can see that there are 14 in the nitric oxide flow control valve and 28 on the oxygen flow control valve. Now these are attached with a kind of a chain. Now this movement of chain with this 14 and 28 teeth will definitely help. They will turn together, and this turning together will maintain a minimum of 25% oxygen flow because teeth are more in the oxygen flow control valve. So this is called as a link 25, and it is to prevent hypoxia. The next hypoxic guard is oxygen ratio monitor controller. It's again a master-slave mechanism, and this is mainly in the Draeger workstations. Basically, here what happens is it is a pneumatic oxygen nitrous oxide interlock system, which is designed to maintain a fresh gas concentration of at least 25%. Now, what this happens is that it limits nitric oxide flow to prevent delivery of a hypoxic mixture. Now, this is interfaced mechanically as well as pneumatically by this oxygen chamber flow. So, if suppose there is a flow in the oxygen chamber and it's a proper flow, adequate flow, the nitrous chamber pneumatically it will move, the diaphragm will move, and it will allow the nitrous to go into the flow meter. But suppose when oxygen delivery is less, or it is less than 25, or it's about 25%, what will happen is pneumatically the diaphragm will not be open and the nitrous oxide will not go into the flow meter. So this is basically a master-slave mechanism. Coming to the flow meter, this is another application of laminar or turbulent flow. We all know that the flow meters or the Thorpe's tube which we are using are the variable orifice. It is basically the diameter is lower at the bottom and then it tapers It tapers in the downward direction, and it is wider at the upper end. Now, the bobbin sits at the bottom until the gas flows. As gas enters, it lifts the float, that is the bobbin or ball, with an upward force from gas below, and there is a downward force of gravity on the float. So it will float until the upward force from the gas flow equalizes the downward force of gravity on the float. It will be constant there. And there's an opening, and the gas flows in this annular opening between the bobbin and the tube. And this annular opening around the bobbin increases with the height. So this is a basic principle of flow meter. Now, this gas flow through the tube depends upon four main factors. What is the pressure drop across the tube, weight and area of the flow, size of annular orifice, and the physical properties of gas. You should always remember that in the lower part of the tube, the flow is laminar. So principle followed is viscosity, while at higher flows, when the bobbin goes up, here flows become turbulent, and the parameter to be used here is density. Okay. The pressure drop across the construction is constant for all positions in the tube, and it's equal to the weight of flow divided by its cross-sectional area. But the size of annular opening is important. The larger the size of the annular opening around the bobbin, higher will be the flow. Similarly, as I told you, the annular space is tubular at low flow rates. Flow is laminar, and the determinant factor is viscosity for the flow, following the Poiseuille's law. While when there's a high flow rate is there, the annular space simulates an orifice, and the gas flow becomes turbulent, depends on the density of gas, and follows the Gram's law. What is the clinical relevance of this turbulence and laminar flow? The clinical relevance for flow meter comes at high altitude, especially. All the flow meters are always calibrated at 760 mm of Hg. Now, since the density of gas is decreasing, but the viscosity is not changing. Now, as higher flows, what happens? I told you that depend on the density as per Gram's law for turbulent flow. Now, at high altitude, the density is less. So, actual flow of gases will be higher than the set flows, because the flow is inversely proportional to the density. So, whatever flow rate we are setting, actually at the higher altitudes, the flow rate being delivered is higher than the set values. And the opposite will occur under hyperbaric conditions. This is the way how the flow meter assemblies, is being assembled. And in first two pictures, you can see that the oxygen is flow meter is upstream. Now, what happens is that if there's a break or leak in the middle of the tube, then part of the oxygen will leak through this middle tube, and the patient will be getting a hypoxic mixture containing more of nitrous rather than the oxygen. Okay. So, and in this picture, you can see that oxygen is downstream. So, this problem can be taken care of, because the leak is of the nitrous and air, but the oxygen is going well. But even with this, even if you're keeping the oxygen flow meter at the downstream level, there is some possibility of hypoxic mixture. Though all oxygen flow meters should be kept downstream to all other gases to prevent hypoxic mixture, but now new technique has been, a wedge has been placed. Now it means the oxygen, the route has been made separately. Now it is not mixing with air or nitrous at any cost. So this will prevent hypoxic mixture more. What is the physical principle behind adjustable pressure limiting valve? It is a part of your intermediate system. And the pressure release valve used during, it's basically a pressure release valve which is used during manual ventilation of spontaneous breathing. Now it opens up at the 5 psi pressure or 300 centimeter of pressure. Whenever there is a high pressure, what happens is that you can see that this seal is closed. But whenever there is a high pressure, the diaphragm moves up, the seal is opened up, and the air is, or any gas is vented out, leading to the decrease in pressure. And this prevents damage to the vaporizers and flow meters. Thank you for having patience. And this, I know it's a big topic, and it needs a lot of concentration to understand the topic. I have left vaporizers in the interest of time, because I had already had taken up a lot of time, and vaporizers can be taken up in any other classes. Actually a very long topic. So once again, thank you, and I would suggest all students to read Ward's, Dosh, and Miller's. Beautifully they have these chapters, and these all physical principles have been described there. Thank you.